All right. I don't have the tests done yet. They're about half done. I'll have them by Thursday. And then we have a quiz at the end of class today. So see what I can get through in about an hour.
I have a question.
Yes.
So the stuff we're covering today, are they included in the quiz?
No.
Oh, okay. So everything from last.
From last class, yeah.
Okay.
Okay. We're still talking about rigid bodies. One thing I want to talk about is equipolant systems. And so it's spelled like this, polant. And the idea of an equipolant system is this. In a rigid body, loads can often, a set of loads can often be replaced by a different set of loads without changing the behavior. One example that we've seen so far, so we've already seen if you have a couple, which is a pair of equal and opposite forces, we can replace that couple with a moment. And we do that every time, so we start to think of a couple as actually just being a moment. But remember, the couple is the pair of forces. We replace it with the moment. We treat it like a moment because it doesn't change the behavior to do that, and it's easier to deal with. Okay. One we won't deal with, one we won't use, is you can always replace any set of loads on a body can be replaced by a force vector at a chosen location. So you choose the location. So whatever loads, there's a million loads acting on this thing. If the body is a rigid body, you can replace all those loads with, choose a position, a force vector at that position. Oh. And a couple. That's a little surprising, and it's kind of cool, but it's not going to be useful for us, so we're not going to talk about that. But if you want to look up a formula for that, it's easy to do. We're going to do one other one. So one we will use. This comes in handy a lot. You can always sorry, not replace. You can always move a force vector anywhere along its line of action without changing the behavior. And I want to emphasize that this is, for this to, equipolant systems only work with rigid bodies. So without changing the behavior of a rigid body. I'll show you why that is in a second, and that'll make sense, I think. So here's an example. If this is the rigid body, and you have a force vector applied at this point, the line of action is the line that goes through the point where it's applied and is parallel to the force. So this is the line of action, and the line of action doesn't stop where the body stops. Mathematically, it doesn't matter. So if it's easier for you in a calculation, you could take this force and move it anywhere along that red dotted line without changing the problem. Okay, a lot of times that'll make things easier. This is the line of action. Notice that it only works with rigid bodies. Like, for example, if you had a lump of, let's say you started with a sphere of clay, and you applied a force here, that's going to cause a deformation in this body, right? If you move that force along its line of action, so you start with this sphere, and the line of action of that force is this. So say you move that force to here. The behavior is going to be different in this case. That clay is going to deform differently. If it's a rigid body, you don't get those deformations, and so you don't have to worry about stuff like that.
Doesn't the position of the force matter in a rigid body?
It doesn't. Well, in some ways it does, but you can move the location of the force along that line of action, and it doesn't change anything. You can't move it anywhere, but you can move it along its line of action. So I'll do an example that shows.
But couldn't you, in theory, move that force along its line of action so that it's not even contacting the object?
Yes, you can. Yep. and you'd get the same answers. Yeah, it's a little surprising, but it has to do with, so it doesn't change the direction of the force vector, moving it along its line of action. So it doesn't change anything in Newton's second law, because Newton's second law doesn't depend on location. The only thing you'd be worried about it changing is the moments in the rotational equation. And moving it along its line of action doesn't affect the cross product that the moment comes from. Okay, so let me do an example. So this is like an exercise that I just invented for this problem. Okay, so this person, you can see how hard it is because of the sweat. Okay, so this person's holding like a handle with a roller on it. And leaning up against the wall with the roller. This is a friction contact because he has such good tennis shoes. This is a roller. The person has a mass of 80 kilograms. And I'm going to give you the center of mass of the system, which the center of mass doesn't have to be on the body. And so the distance from the contact point to the center of mass, we'll call that 0.5 meters. And the height from the floor to the roller is 0.8 meters. And we want to know what are the reactions. Well, the first thing we have to do is a free body diagram. Nope, we have everything we need. So I'm going to show how this works. We're going to use that equipolant systems thing. All right, so at the center of mass, there's a weight. So that weight is acting at a place that there's no person. That's 80 times 9.81, which is 784.8. And now we go around the boundary looking for contact. At the roller, there's a contact perpendicular to the surface that it's rolling along and toward the chosen body, so I'll call that N. And then go around the outline and you get to the feet. This is a friction contact, so that's an unknown force vector. I'll call it R. And I'm going to set up the full pancake table. So pancake, artist, row, 4, marzipan. let's put the origin down here at the feet. Okay, so let's just go through these forces one by one. What is the position vector? What are the coordinates of the point where that force R is applied? That's the origin, yep. I'll write it like that. And we have to choose an about point. We might as well choose the origin for that too. And so subtract P minus A to get rho. You get zeros. The force vector is Rx, Ry, 0. And the cross product of 0 with this is 0 vector. Now we get to the weight force. We know the horizontal coordinate. What's the x coordinate of the point where that's applied? Yeah, 0.5. But we don't know anything about the height. So what should I guess I'll just call that h for now. The about point is the origin. Subtract, and you get a row vector of 0.5, h, 0. The force vector of the weight is 0, negative 784.8. And if you take that cross product, you get 0, 0, 0.5 times 784, negative 392.4. And now the this force N, that roller force, we know the vertical coordinate. What's that? 0.8. But we don't have a horizontal position. There's nothing given that tells us how far away horizontally the wall is. So I'm just going to call that W. So we have W 0.80. The about point is the origin. Subtract, and you get a row vector of W 0.80. And the force vector, that's in the negative x direction, so that's, yeah, negative n, 0, 0. Take that cross product, and you get 0, 0.8 n. Okay, so we'll write out Newton's laws. The first one, Newton's second law, says Rx, Ry plus 0, negative 784.8 plus negative n, 0 is equal to zeros. And the moment equation says 0 minus 392.4 plus 0.8 n is equal to 0. So what we have is Newton's laws have no dependence on h or w. That's surprising. I mean, h and w are H and W are part of the locations of those points. But what we have is that since there's no dependence on the height of this point, that's H, you can move this force anywhere along its line of action and get the same answers. And since there's no dependence on W, you can move this force anywhere along its line of action and get the same answers. Yep.
Just so I'm clear, because I'm still a bit confused on this.
Yeah.
Even though this works out in calculations, you still wouldn't be able to do this. You still wouldn't be able to move that force in reality, correct?
In reality, if the thing adequately behaves like a rigid body, so if deformation isn't a big part of what you're trying to calculate, then yes, in reality you could actually physically move those forces. I'm talking about this, though, as a way, like the calculations we do, the forces are given, and this is a mathematical thing we can do.
Simplify it.
Yeah. You could also move those forces physically. We usually don't have that control in this class. Was there another question? Okay, so what that means is instead of calling the location of this force the weight force here, we called the location 0.5H0. I could have moved it along its line of action to 0Y and just called it 0.500, and we would have gotten the same answers. And this one, instead of saying it's acting at W.80, I could have moved it along its line of action to x equals 0 and just written it as 0.80. We would have gotten the same equations. Yep.
Is it true if it's, are we ever going to see a situation where the line of action is in the z-axis?
Yeah, we are. We haven't talked about 3D stuff yet, but that's sort of the next topic we're going to go into.
Is it still motivated?
Yes. Yeah, it's a property of the cross product. So basically, the cross product only cares about the perpendicular distance of that, like the perpendicular length of that row vector to the line of action of the force. That's all that cross product cares about. And so everything else is just extra. Okay, so let me draw this again. So we could have treated this problem like so the free body diagram looks like this. The origin is here. We have a force vector, R. That's the friction contact. We have a weight force that now I'm going to put here. And we have a roller force that now I'm going to put here. And so the pancake table, pancake, artists, row, 4, marzipan. The location of that friction contact is still the origin. Make the about point the origin. Row vector is 0. Force vector is Rx, Ry. Moment is 0. Okay, so now what's the location where that weight force is applied? Yeah, 0.5 and then zeros. The about point is still 0. The row vector is 0.500. The weight is 0, negative 784.80. The moment is 0, 0, negative 392.4. And now what's the location where that normal force is applied? Yeah, 0, then 0.8 was the height, 0. The about point is 0. Subtract and you get 0, 0.8, 0. The force vector is negative n, 0, 0. Cross product says 0, 0, 0.8, n. And Newton's laws are exactly the same. Any other questions about that? Okay, so now we're going to extend this to 3 dimensions. So 3D rigid body statics. The big picture is the approach stays exactly the same. You can still use the pancake table, the abbreviated, that shorter version of the pancake table. But what changes is in 2D, Newton's second law gives how many equations? How many useful equations? 2. The moment equation gives how many? 1, yep. In 3D, how many equations does Newton's second law give? 3. And how many does the moment equation give? 3 also. Yep. So, so in 2D you get 3 equations. In 3D you get 6 equations. So in 2D, how many variables can you solve for? 3. How many variables can you solve for in 3D? 6. Yep, exactly.
Is it much harder?
The thing that is harder about it is dealing with the joints. And so I'm going to go through a list of the joints the same way I did with 2D, and maybe these things will help visualize them a little bit. In 3D, we draw the couples differently. doing them like this. So now we have couples about every axis. And so drawing them like as a rotation like this about each axis would clutter up your picture and be really hard to do in a way that looks good. So this is how we did it in 2D. In 3D, we'll do it as, it'll look like vector components, because that's what it is. Moments are vectors, and they have components. But instead of a single arrowhead like we use for forces, we're going to use a double arrowhead like this. Okay, so what this says is this is the x component of the couple vector, y component of the couple vector, z component of the couple vector. What?
The math is backwards. I guess the Z is the top one.
Oh.
3D plane.
Well, you can draw it in different ways, as long as you have a right-handed coordinate system. But yeah, whatever your coordinate system is, the couple component in that direction is that component. The main thing that gets harder in 3D is working with the joints. Okay, so I'm going to do one example where we don't have to do that yet. All the loads are just given. And then we'll go into the joints in 3D. Okay, so let's say that this is the rigid body. It has a mass of 60 kilograms. And it has a length this way of 1 meter. It has a length into the page of 0.5 meter. And it has a height of 0.5 meter. And for loads, right in the middle of the front face, there's an unknown force vector, F. On the top, you know what? I'm sorry. That's an old picture. So actually, instead of putting that in the middle of the front face, that force has to be in the middle, but along the top edge of the front face. I'll call that, call it F. And then in the middle of the top face, we have a couple with a component that way of 100 Newton meters and a component up of 300 Newton meters. Then also on the front face, we have a force vector with a y component and a z component, but no x component. And then the last force, besides the weight, is this force vector B that has x, y, and z components. So I'll just call that a B vector. And then there's also the weight that's acting at the center of mass. And that is 60 times 9.81 is 588.6. And we want to calculate F, AY, and AZ. And the B vector. So first, just thinking about the number of variables and the number of equations, do we expect that we should be able to solve this? Yeah, because we have 6 variables. We know we're going to get 6 equations. It doesn't always work out because some could end up being redundant or whatever, but it looks good at this point. So let's start filling out the table. As an about point, let's choose this, because it's where we have the most unknown forces. And let's choose a coordinate system. Let's call this the x-axis. This the y-axis, and this the z-axis. Yep.
So, because your diagram has like all the things that we would need in the free body diagram, you're not doing free body diagram?
Right. This is the free body diagram.
We could draw them in 3D, the free body diagram.
Yeah, in 3D you have to. In 3D it's hard to make it look real clean.
Is there a joint to this? Like, is there
No, so I just, basically I've already taken the step in this problem of taking the joints and expressing them as loads. So this would have been a joint, and this would have been a joint, and this would have been a joint. Okay, but I've already taken that step, so first we can just see the math work, you know. Okay, so let's do this just as, so calculate the row vector, calculate the force vector, calculate the moment. And we're going to do this just one by one for each load. So we'll start with that force vector B. The row vector goes from the about point to the location of the force. So what's the row vector for B? Yeah, so it's just 0, that's right. And the force vector has all 3 components, so Bx, By, Bz. If you take the cross product of those two, you get 0 moment. That's why you like the about point to be at the place with the most unknown forces, because you're always going to get no moment from those unknown forces, so they won't appear in the moment equation. Okay, so now let's go to the weight force. The row vector for this point here is, well, we have to go halfway along this 1 meter length to get there, then we have to go back halfway along the 0.5 meter length to get to the middle of the bottom face, and then we have to go past that height of 0.5 meters to get up to the center. So it's going to be, in the x direction, it's going to be negative 0.5. In the y direction, it's going to be positive 0.25. And in the z direction, it's going to be negative 0.25. Anyone have any questions about how to get that? So just think, in these 3D problems, you just have to think, how far do I have to go along x? Then how far do I have to go along y? Then how far do I have to go along z? And you're just going to zigzag your way to the point. 1, 2, 3. It's always those 3 steps. The force vector. Question? So the force vector is 0, negative 588.6, 0. And if you take that cross product, you get 0, 0. No, you're right, it wouldn't be. I'm just used to saying that. For x? Negative 147.15, okay. And then 0 for y. And then z would be positive 392.4. No, 294.3. 294.3, okay. That one would be positive. Okay, and now that force F. So how far, to get to F, how far do you have to go along the x-axis? That's right. Half a meter in the negative x direction, and then how far do you have to go in y? 0.5, and then how far in z? 0, yep. So minus 0.5, positive 0.5, 0. And the force vector? It's in the positive z direction, yep, so 0, 0, f. So you get 0.5 f, and then positive 0.5 f again for y, and then 0. And now the couples. I showed the couples as being at a specific location, but remember the couples don't have any dependence on about points or anything. So we're just going to add those couple components into the moment column. Yep.
You didn't do the AY, AC?
Not yet, right.
Just wanted to make sure you hadn't forgotten it.
Okay, yep, yep. So for the couples, we don't care about rho, we don't care about F. We're just going to write that in as a 100 and a 300. So 100 in the positive x, 300 in the positive y.
So when do you apply the Newton's third law on the couples? Like when?
If you're going from, so if those couples were created by contact with another body, and then you isolated the other body, then you would use Newton's third law. I think it's the case that we're not going to do that in 3D. I don't think there are any problems actually where you have to use Newton's third law in 3D just because of the problems we're doing. And then the last one is AY and AZ. How far along X do you have to go to get there? Just the full 1 meter in the negative X direction, and then you're there. So the row vector is -1, 0, 0. The force vector is 0, AY, AZ. And the moment is 0, and then positive AZ, and then negative AY. So Newton's second law says Vx, Vy, Vz plus 0, negative 588.6, 0, plus 0, 0, F, plus 0, AY, AZ is equal to zeros. And then the moment equation says -147, 0, 294. Plus 0.5f, 0.5f, 0. Plus 100, 300, 0. Plus 0, AZ, negative AY. Is equal to zeros. And so if you write out a matrix for this, we have 6 equations. We have 6 variables and then a constants column. So this is equation 1, 2, 3, 4, 5, 6. And for variables, let's do Bx, By, Bz. Then F, and then AY, AZ, and then a constant. Okay, so equation 1 says Bx's we have 1, everything else is zeros. Equation 2 says By's we have 1, AY's we have 1. And the constant has to be on the other side of the equation, so that's positive 588.6. Everything I'm not filling in is a 0. The third equation says BZ's we have 1, F's we have 1, AZ's we have 1, and nothing else. The fourth equation says F's we have 0.5, constants, we have positive 47.5, 47.15. The fifth equation, F's we have 0.5. AZ's we have 1. And constants we have negative 300. And then the sixth equation, AY's we have negative 1. Constants we have negative 294.3. And what I have written down for this, for solutions, is the B vector is 0, 294.3, 252.85, the value F is equal to just 94.3. And the A vector, well, that's, I have it written as vector components here, but we know it isn't going to have an X component. And then 294.3 and negative 347.15. Any questions about that? So notice that when you go to, in 2D you have 3 equations. Solving that by substitution isn't too bad, but switching to 3D, you just probably want to write it out as a matrix. You don't want to be doing a system of 6 equations by hand. The next thing we're going to go into now is, so that's how to do the problems once you have the free body diagram. But in order to get the free body diagram, you need to be able to translate the joints into loads. So the next thing we have to talk about is 3D joints. And I think maybe what I'm going to do is just do we'll just start the quiz. But we'll do this like we did with 2D joints. We'll just go through starting with joints that introduce one variable, and working up to a fixed joint, which was in 2D, remember, a fixed joint introduces a full force vector and a couple because it doesn't allow any motion. In 3D, it doesn't allow any motion either, which means it restricts translation along all 3 axes, and it restricts rotation about all 3 axes. And so a fixed joint, in this case, introduces 6 variables. Any questions about any of this? Okay.